Hello everyone, welcome back to the lecture series of Learning Theory of Automata and Formal Languages. My name is Binaya. I am working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College. So we are into the last portion of unit number 2, where we have tried to cover up, or we have tried to showcast almost all the things regarding the concept of theory of automata and its regular expression part also. So this is actually unit number 2 and this is lecture number 16, where we are going to study about the last part of our regular expression part, where we will try to understand how a particular language can be identified as a regular language. Okay, and also how to identify that language is not regular. If not regular, what is the process? Everything we will try to cover up in this video. Okay, so let's check it out. What and all are the topics? So in this lecture number 16, we will try to understand the concept of regular as well as non-regular languages, how to identify that a language is regular or not. This is very important actually if you are going for university point of view, or if you are going for any kind of competitive exams as well. Okay, so this is an important point. Then if you are having the use of pumping lemma also, now this particular topic, that is pumping lemma, we will try to understand once we cover up this particular topic. What is this pumping lemma? Why we use pumping lemma? Everything we will try to understand in this particular video. So let's check it out. What is the concept behind regular language? First and foremost thing is that before going into the language, let us understand the hierarchy once more. If we have covered up in the earlier video lectures, then you should have understood that. But just I am trying to cover up this particular concept so that you can relate on it. Okay. Actually, before going into this particular topic, we need to understand what is the hierarchy of it. Okay, what is the hierarchy of these languages? The languages generally starts off with regular language. Some demerits were there, there is no, we can say not possible also in some cases, for which we have covered up into one more language which is known as context free language. I am just writing out in the short form. We will learn this hierarchy in a proper way in unit number 3. Okay. Thereafter, we have to understand context sensitive language. There are some properties, some issues in the context free language part, for which we have covered up in context sensitive language. And finally, the most powerful language is recursively enumerable language or recursive language. Recursively enumerable language. So this is the highest, the most powerful one, and this is describing the language part of it. But if we look into these languages properly, okay, we are having some sort of acceptors also, which we have learned. Acceptors like finite automata, which may be DFA, NFA, Milli, Murray. Okay, CFL, accepted by push down automata. Okay, PDA, or short form is PDA. Here, acceptor is linear bounded automata. Okay, and finally, here the expression acceptor is Turing machine, which is the most powerful machine. Okay, now these are the acceptors which are accepting these languages. Definitely, there will be some sort of generators which will generate the strings of this language, and those generators are regular grammar, context free grammar, context sensitive grammar, and then unrestricted grammar. There is no restriction in the grammar. Every possible strings in the universe can be generated from this grammar. Okay. So overall, I think I have tried to make you understand. This is the generator part, this is the language part, this is the acceptor part, and in the case of regular language, we are having a representator also, which we have already understood till now, the regular expression. Okay, now the concept comes here. This is the hierarchy. Okay, and this is actually the hierarchy is like this: that regular recursively enumerable language is greater than CSL, powerful than CFL, and then CFL is powerful than regular language. Okay, this is the hierarchy, and this hierarchy was given by Chomsky, Noam Chomsky, and we will learn about this hierarchy named as Chomsky hierarchy in unit number 3 properly. Okay, now why I have mentioned this thing is that I will be given a language to you, or I will be giving a language to you. You need to identify that whether it is a regular language or CFL or CSL or REL. We will not cover that whether it is CFL, CSL or REL. We will cover it later when we will be learning these topics. But as of now, we will try to understand that whether this is a regular language or not, which language I am giving it to you. Okay, so let's check it out. Okay, now what is a regular language? A language is said to be a regular language if and only if finite state machine recognizes it. I have already mentioned you, right? Acceptor should be finite machine. So what languages are not regular? If the language is not accepted by finite state machine, the languages which are not recognized by finite state machine, and second and the most important is that the finite state machine which requires memory. How and what is the concept behind this memory? We will try to learn with some examples. Okay. Now I have given one particular question, number 1, a to the power n and greater than equals to 0. Let us look into this particular language and let us try to understand that whether we will be able to design a machine for it or not. Whether we will be able to design a finite state machine for it or not. Okay. See, this is a to the power n. This means what? This means a to the power n greater than equals to 0. So a to the power n means a to the power 0, a to the power 1, a to the power 2, and it will keep on going. So if we look properly into this diagram, can we make a finite state machine where there is a self loop of a? Yes, we can make it, correct? This is a simple loop, but if a to the power 0 means what? A to the power 0 means epsilon. That means initial state should be final state. So can I make this as a final state? Yes, I can make it. So I can make or I can design a finite state machine for this particular language irrespective of the concept that we are not include any kind of memory part. Memory means or counting means or comparing. These three things should be remembered by you: memory or counting or comparing. I will let you know about this. But here it's not a memory concept. See, whatever, if I say n equals to 5, then a will be running for 5 times. There is no memory concept. Like memory, when it will come, when I am trying to compare with someone. Suppose I am trying to compare a to the power n, b to the power n, and n value is similar. So if I give n equals to 50, then the machine should remember that yes, 50 times a will be traversed. After completion of 50 times a, b will be starting. That time the concept of memory comes. Here there is no concept of memory. It is just simply running the machine with a loop of a. That's it. So if we can design a finite state machine for this language, then this language is what? A regular. Now I have put some of the important points on it. So one particular shortcut you can remember: if power is equals to 1, or you can say means single power. It's not is equals to 1. It's a single power. Okay. Then always it will be a regular language. Why? No memory comparison. There is no comparison, right? No counting and also no storing and saving. There will be an input tape, okay, where a will be there, okay. Just it will keep on checking, keep on reading a. There is no concept of storing and saving. That's it. So this is all about your first one or first power, logic, that if single power we are having in a language, then definitely it will be a regular language. So I have mentioned here, does it is acceptable by finite automaton. Sometimes a question might comes to you that whether this language is a regular or not. You need to properly mention in this format while writing in an examination point of view. Next, check. Let's number 2 point. If there are two different powers, okay, if there are two different powers, then it will always a regular. Why? See, n and m are both different things, right? So if n and m are both different values, then definitely a to the power n and b to the power n are two different powers. So there is no concept of what? Memory comparison with each other. First it will run for a. Suppose I have given n 5 times, then definitely 5 times a will be read. I have no issue with b, okay, because m value I will be giving suppose 7, then 7 times b will be running. So there is no concept of memory comparison. Then also we are not having any concept of no counting, nothing count. Counting in the sense means I have to count for 50 times, then b will be starting. That is not issue. There is no that is not the concept of it. Here we just need, we have given n equals to 5, then 5 times a will be running. No issue about that. But there is no counting and comparison over here. Okay, I mean to say that counting and comparison. Next comes no storing and saving. It will simply scan. So therefore, this is an acceptable one. Let's go to question number 3. It says, see, powers are same. Now the concept comes is powers are same, but the language is finite. See, when the condition is finite but powers are same, then it will always be irregular. You just think of it that I know that n always I have given 20 to the power 3. So this is a finite value. I have not given that n greater than equals to 0. I have given less than equals to 20 to the power 3. So I know that the maximum to maximum this machine can run A for 20 to the power 3 times. After that, automatically B will be starting. So I can design a machine for it. So therefore, no memory comparison will come, no counting and no storing and saving. And therefore, we can say that this language is a regular language. Clear? Now comes to the next point, which is an important one. And this will be what? This will be a point to be noted, that if the same powers and also it is infinite, the condition is infinite, then will be not regular. I have already mentioned, I have already described about this, that if a to the power n, and I haven't given that n value can be anything. In this scenario, n was restricted to 20 to the power 3, so it was already a finite. But here we cannot say that what is the concept behind n. N can be any value, correct? So if it is any value, it can be infinite also. So I doesn't know the memory. There is like memory comparison will be required. The next counting is also required. If memory comparison is there, I need to count how many times A has finished and then B will be starting. Correct? That concept, that capacity is not there in the case of finite state machine. And also storing and saving is required. See, A to the power n, B to the power n. I have to run first of all A to the power n. Okay. And n value is not stagnant. And n value is also infinite. So by anyhow, I can say that this A will be running, or this A will be running without knowing that how many times it will be running, because finite state machine doesn't have the concept of memory comparison. Neither they are having the concept of counting along with comparison. Okay. And also we are not having any extra data structure in the case of finite state machine. Only the input tape is the data structure. And that will not help in the case of this kind of string. So therefore, we need to sum up these points and we can disclose that this is not acceptable by a finite automata. Okay. And last, I have also already mentioned this particular concept. Okay. So this is what I have tried to make discuss with you all. I have tried to make and discuss with you all few of the things like a to the power n if single power. Okay. We have tried to discuss with you all about a to the power n, b to the power m if different powers. Then I have tried to discuss that with you all a to the power n, b to the power n, but n condition is finite. Okay. Then we have discussed with you all a to the power n, b to the power n, but n condition is infinite. Okay. So these are some of the basic rules in order to identify that whether a language is regular or not. Okay. Let's discuss one more category or one more algorithm in this syllabus, and that particular topic is known as pumping lemma. Okay. Actually, this is a particular algorithm which is a proof, okay, for irregularity of a language. Okay. Actually, it's a negative algorithm. Okay. Let's check what is all about it. Pumping lemma is used as a proof for, I told you, irregularity of a language. Okay. Thus, if a language is regular, it always satisfies pumping lemma. If the language is regular, it's perfectly fine. Pumping lemma, as it is a negative algorithm, it will always be accepted. If there exists at least one string made from pumping which is not in language, and this particular concept we need to check it out along with the example. Okay. Otherwise, you will not be able to relate that exist at least one string from pumping. What is the meaning of it? We need to check this concept only with an example of it. Okay. Which is not in, then L is surely not regular. Now, this particular point we have to skip over here because we need to discuss one example, then only we will be able to understand this. Okay. Next paragraph, the opposite of this may not always be true. That is, if pumping lemma holds, it does not mean that the language is regular. Okay. So, all of a sudden we can understand that this pumping lemma is a negative algorithm which is used to prove that a language is not regular. Okay. Let's check it out. What is the algorithm steps for this example, for this algorithm, and discuss an example on it. We have discussed this example and we have disclosed that if in a language we are having same powers, okay, and the condition is also infinite, then definitely the language is what, not regular, correct? So we need to prove it. Okay, how do we prove it? By using pumping lemma. Let's check the steps. Step number 1 says that let A be a regular and a pumping length be P. Therefore, see, A, considering A, or you can say L. Here we have mentioned as L, so let me mention as L only. Let this particular language be regular, okay, in an optimistic manner, okay. And I have also mentioned that it's a pumping length be P. Therefore, already it's n which is greater than equals to 0 means what? It's a infinite language, right? Infinite length. So I have restricted the length. I have taken a pumping length called P, okay, and this is completely based on the user, whatever value you want to give it in order to prove the condition, okay. Next, in step number 2, we need to choose a string. We need to choose a string in this format. Now it will be not a to the power n, b to the power n. I have taken a pumping length P, so it will be a to the power P, b to the power P. Okay, clear? And divide the string into 3 parts, x, y, and z. Means this particular string we need to divide into 3 parts, x, y, and z. Okay, this is about step number 2. So I have divided. Now in step number 3, this pumping length that I have taken, I need to assign a value for this length. Suppose in this particular step number 3, I have assumed P is equals to 7. Now if I have taken P is equals to 7, then S, or this I have taken, the string I have taken, it will be what? A to the power 7, B to the power 7. So A 7 times, B 7 times. Okay, now the string will be this one. Okay, I have taken this one, but from that I have taken the particular string of this format. Okay. Now in step number 3, I will do certain cases. See, the condition behind dividing this particular expression into x, y, z is why I need to finally check this particular condition according to this algorithm. X, y to the power I, z. Okay, how? I will let you know. See, because of this, we are doing 3 cases. If you look into this particular scenario, which is the variable which is varying, means which is the variable which is varying actually. If you look into this expression, y is the variable which is varying. See, y to the power I. So that means what? Y is the one whose value will be changes, but x and y, z will be remaining constant. Okay. Now let's check it out. So that's why I have taken 3 cases where only I have considered y case. Let y be in A, let y be in B, and let y be in both A and B. First I will take y in A part, next I will take y in B part, and in third cases I will take y in both A and B. Okay. So I have taken these 3 conditions. Okay. In these 3 conditions I have taken let y be in A. So I will take last 4 of this one as y. This will remain as what? X, and remaining part will be what? Z, as it is x, y, z. Clear? Next, in second case y in B part. Y in B part. So I will take, suppose, first 4 as B as y. After that it will be what? Z, and these A will be what? X. Okay? Clear? Now next, y in both A and B. So I have taken 2A as y and 2B as y. Remaining will be what? Z, and this will be what? X. So these are the 3 cases I have divided, and these are the possibilities I have taken. Clear? Now in the step number 4, I will take, see, here I am having these variations in y, right? So y is having the power to the power what? I. So if I have taken a particular, or if I restrict a particular value to I, then I can choose, and then I can check whether this particular string is behaving in the same way as like according to the language or in a different way. Okay, so what I have done, I have taken in step number 4, I value either 2 or 0, whatever you want. Okay, so let's check again the cases. Now the cases will be x, y to the power I, z. Okay, if you look into case number 1, y was what? S was what? S was 3 times A. Okay, then A to the power 4 times and B to the power 7 times. And these A 3 times is for what? X. This is for what? Y. This is for what? Z. Okay. So a to the power 3, b to the power a to the power 4 and b to the power 7. Now if I take y part, okay, y to the power I, y to the power I, and I value I have taken as 2, then it will be what? Then it will be s will be what? X is what? X is a to the power 3, okay. Y is what? A to the power 4. Now it will be what? A to the power 4 plus 4, double, it will be double, see, it will be double. So it will be 8 and then b to the power 7. So therefore total it will be a to the power 11, b to the power 7. Clear? So this is what I have got after taking or after varying the value of y. Earlier it was like this, and now I have got this one. Now does this particular scenario accepts this language? Because n are different here, a to the power 11 and b to the power 7. So n value is differing. So therefore this is not accepted. Clear? Next comes case number 2. Here also see y to the power 2. Okay, let's check what is the initial value of s over here. S will be x, all a7 will be x, okay. Then b 4 times as y. So b 4 times as y and remaining b 3 times, correct. Now if I apply y to the power 2 over here, then it will be what? A to the power 7, b to the power 8 and b to the power 3. So it will be a to the power 7, b to the power 11, and this also contradicts with our given language. So this case will also be not accepted. Clear? Next comes this particular part. Here it will be what? S is equals to a x, for x it is 5 times a. So a to the power 5 and a to the power 2, okay. B to the power 2 is for what? Y, and b to the power 5 is for what? Z. I have just extracted this part in this format. Now look into this. Here also y is equals to 2. So what will be the format of it? See, x a to the power 5, it will remain as it is, it will be constant. Y is what? A to the power 2, b to the power 2, double. So the format will be what? A to the power 2, b to the power 2, a to the power 2, b to the power 2. Correct? So therefore finally b to the power 5 as y, as z. So it will be b to the power 5. Now look into this particular scenario. Overall if you look, what is the value of a 5 plus 2 7, 7 plus 2 9, and b is what? 2 plus 2 4, 4 plus 5 9. So overall it is matching with this particular language, but does the format is matching? The format is not matching. Why? It should be what? After completion of a, b will be starting, right? In the given language. But here what is happening? After completion of 7 a's, again b is starting, again a is coming, again b is coming, and it is ending with b. So the format is not matching with this given language. So this will also be rejected. If all the cases rejects, then we can say that yes, the final given language is not regular. And this is the way of dealing with pumping lemma questions. First, you need to find out, you need to disclose that the language is irregular in an optimistic way. Then I have to disclose a pumping length. Then I have to divide this particular string into 3 parts x, y, z because of this scenario. I have to take 3 cases. Why? Because y is having a variable over here, and y I have taken in a first, in b, and then both in a and b. Then I got some sort of like this type of expressions in all the 3 cases, and then I have applied y I value into 2 or 0. Any one of it you can take it, and then you check the cases whether it is matching with the given format or not. If it is matching, then this language is regular. If not, then it is not regular. Definitely will get the condition as not regular only. Okay, because pumping lemma is a negative algorithm. It is used to check the irregularity of a language. Now I hope you can understand this particular line, that if there exists at least one string made from pumping which is not in length, then the L is surely not regular. Which I have got after pumping length, we have got the different type of category, correct? So this is where this is the particular topic which we have tried to understand, and this is actually used for checking irregularity of a language. Okay, so in this video we have tried to understand how to identify a language is irregular or not, Then we have tried to understand the concept of pumping lemma, with the help of which we can understand that a that a language can be declared as a irregular or non-regular. Okay. So this is all about your unit number 2. In the next upcoming video lectures, we will start off with a new concept. So thank you for watching the video.